Good evening, students, and welcome to today's session. So we will continue ahead with system of particles, discussing about center of mass and applications of integration in the calculation of center of mass as we were doing in the last lecture. So let's begin. Right. So as we were discussing the previous lecture, we were looking at center of mass and the position of center of mass by the application of the formula integration RdM divided by total mass for a continuous mass system. Then further we understood that this particular formula, depending on the type of mass distribution that we have, whether it is a linear distribution or it is a surface type of distribution or it is a volumetric distribution, the quantity, the differential mass dm has to be taken as a linear element or correspondingly a surface element or correspondingly a volume element, where accordingly the quantity lambda becomes linear mass density or mass per unit length, sigma becomes surface mass density, or rho becomes volumetric density, or simply what we call density or mass per unit volume, like that. So in that we had seen a few examples of linear distributions of mass, and then we had moved on to look at one example of surface distribution of mass in that triangular lamina. So let's continue with another example of surface mass distribution. So next example we will look at here today is going to be next example we'll look at is going to be center of mass of
Sorry, sir, it by mistake
semi.
happened.
Sorry, come again, Rita.
Sir, I have done that by mistakenly.
That's okay. So center of mass of a semi disk, okay, which is basically a thin, uniform semi disk shaped lamina. Lamina means a two-dimensional surface. Okay, lamina is any surface in a two-dimensional plane, okay, like a disk or a square or any such surface which is, whereas non-laminar surfaces are surfaces that in three dimensions. Okay. So for example, a spherical surface or the surface of a cone, okay, or cylindrical surface. These are examples of non-laminar surfaces. Okay. Whereas any surface that is lying on a 2D plane, that is called a lamina or a laminar surface. Okay. So semi-disk is an example of a laminar surface, but it also has a high degree of symmetry. So let's see how to calculate the position of center of mass of a semi-disk. So basically you can think of it like this, that we have cut out a disk made of some uniformly distributed mass. Not really, I mean, it was, Archita, it was just a quick recap of what we've learned in the last lecture. So you can ignore that part. Okay. So if we take a disk made of some material which has uniform mass distribution, a thin disk like a cardboard crust or a plastic sheet or something like that, and you cut half of it exactly, You cut it along a diameter. Then the shape we get is what we are talking about over here. This is, let's say, this is where the geometrical center of the original disk was. So this is a thin uniform semi-disk of mass m and radius r. So this radius here is r. Now we want to find the position of the center of mass. Okay. So once again, one thing you can identify here is that the y-axis is an axis of symmetry. So the center of mass will have to lie on the y-axis.
Sir, this is an example of
Y-axis.
surface or linear
Yeah,
distance.
it's an example of surface. No? You can see it's shaped like a lamina. No? So the mass is distributed over a surface. No? Okay. So it's
Okay.
the y-axis, right? Y-axis is a symmetry axis because it bisects the given surface, bisects the surface into identical, on either side of it is identical shapes, quarter circles, quarter discs rather. So that means the center of mass will lie on the y-axis as we discussed last time. If you can find any axis of symmetry, then that's one thing less, because you know that center of mass lies on the y-axis. Okay, at a point, let's say C, whose coordinates will become 0, ycm. So now we have to find this y coordinate of the center of mass, where the origin is the center of curvature. Okay, so this will become the task in hand. So obviously we'll find ycm by using this formula, integration ydm divided by total mass. But here dm should be a surface element,
Sir,
because the disk, yes,
sir, what did
yes, tell
you,
me better.
sir, what are you discussing? Because I had to face a technical issue from my side.
Sorry, come again, I can't hear you properly.
Sir, so what did you just discuss now? Because I just lost my connection.
Yeah, what we are discussing is there on the board, beta. We are discussing about the position of center of mass of the semi-disk, which is a laminar surface. Okay, so we are trying to calculate the position of center of mass of a semi-disk. Like in the last lecture, we had calculated position of center of mass of semi-ring. Okay, but that was a linear distribution. Now this is a surface distribution. Okay? So that is why dm is going to be a surface
Okay, sir.
element, because the semi-disk is a surface distribution of mass. Okay, so just take down the important points up to here, then we'll see how to continue further with this. Okay, now when it comes to surface elements, you can see dm will be equal to sigma into dA, where sigma is the mass per unit area, right, which is what we call the surface mass density. So sigma over here will become how much? It will become m upon pi r square by 2, because the total mass of the disk was m, and the surface area of the disk is half the surface, rather surface area of semi disk is pi r square by 2, half of the full disk. So this is the mass per unit area. But now for dA, we have to understand. Okay, so we have to figure out what type of differential element to consider. What kind of differential element we can consider, so that we can substitute properly. Okay. So now for this we have two options. Okay, for the differential element, we'll discuss about that. So the two types of elements we will consider are going to be like this. Okay, just bear with me a moment, we'll get the diagram correct. Okay, so one option we have for our differential element is that we can slice our entire semi disk into thin semi rings like this. So they are concentrically placed one on top of the other. Okay. So that is one option that we have. So this is our y-axis. This is our x-axis. This is our center of curvature. Okay. Now we can consider radius r and thickness dr. Okay. This can be our differential surface element. Okay. This can be our dA as a thin semi-ring of radius r, thickness equal to dr, and therefore area equal to pi r into dr. Here we are using the concept that area is equal to length of the semi-ring into thickness. So it's like we've taken a rod of length pi r and thickness rather pi small r, and of thickness dr, and then we bent that into a semi-ring like this.
Sir,
Yes. Okay. So the area is length into thickness, so it is pi r into dr. So one option of taking the area element is like this. Yes, tell me.
sir, that we cannot cut that area in horizontal way.
Yes, that is the second option. So as I told you, we have two options. So we have to see what is going to be more convenient for us. But both the options are going to be okay to calculate the center of mass position finally. But this is one option we have, and why I have considered this option is because in the last lecture we have discussed the position of center of mass of a semi-ring. Okay. So notice the mass of this semi-ring. So this differential element, it will have a mass dm of sigma into dA. Okay, so that is 2m upon pi capital R square into its own area, which is pi small r into dr. So dm is going to be 2m upon capital R square into r dr. Okay. But we also know that this ring, a semi-ring, has center of mass at y equal to what position? 2r by pi. Remember, we discussed this in the last lecture. The position of center of mass of a semi-ring was 2r by pi on its y-axis. Okay. So we can replace this semi-ring of mass dm and radius small r with an equivalent particle on the y-axis. But that particle should be placed at what position? It should be placed at a position of y equal to 2r by pi. Okay, so we'll come back to the horizontal strip method also. We can do that also, but we'll see that this is ultimately going to be a little bit more convenient. Okay, so let's understand this first. So what we are doing is we are slicing our semi-disc. We are slicing this into semi-rings like this, thin semi-ring after the other, and each semi-ring is like a differential mass dm, whose own center of mass is located where? It's located at this position. So each of these semi-rings will be replaced with a collection of particles lying on the y-axis, okay, whose mass are individually this and whose y-coordinate are individually this. So then we can use the integration formula, integration y dm divided by total mass. In that we can replace y with this. Okay, we can replace y with this formula, and we can replace dm with this formula and just integrate for all the semi-rings. Understood, no? Okay, so I'll just take you back to the previous section once more, so you understand what we are doing over here, and then we'll see the execution of what we are doing below using the semi-ring as our differential element. Okay. So we are finding the center of mass of a surface distribution, which is a semi-disk. So first thing we notice that, okay, the y-axis is an axis of symmetry. So once we know the y-axis is an axis of symmetry, we know the center of mass of the whole thing is lying somewhere over here. It's here at some coordinate 0, ycm. So now our job is to find the position of the center of mass. So for that we have to use this formula, and in this formula we have to replace dm with a surface element sigma dA. So sigma is easy because it's a uniform distribution of mass, so it's total mass by total area. But what we should take as dA? That is the next question. So the answer to that question is we should take a dm or a dA as an element which is having the same symmetry. It's symmetrical about the y-axis. So one option would be to cut horizontal strips, so because they are symmetrical about y-axis. Another option, which is quite useful, is that we can slice it into semi-rings like I've done over here. So if I do that, then this is how I should replace dA, and this is how I should replace the y-coordinate of that particle dm in the formula integration y dm divided by total mass. Okay. So just make a note up to this step next, and we will continue from here. Now, once you've done this, you'll see the integration is very easy. So that is the advantage of using this method of semi-rings. The integration part becomes very simple. Yes. So Norman, that is a formula that is coming from our previous lecture. Okay. So let's just take a look at that once again. Okay. Center of mass of a semi-ring.
Sir, how
Yes.
that y equal to 2r by pi?
वही बता रहा हूँ, just explaining that. It's a formula that you have to memorize from what we have discussed in the last lecture. If you have a semi-ring of mass m and radius r, the position of the center of mass, we are done by integration last time, ना? इसका center mass यहाँ पे होता है. So this y coordinate is how much? It is given by the formula 2r by pi. In fact, this was another application of a more general formula, where if you have just an arbitrary arc which is subtending some arbitrary angle alpha at the center of curvature, this angle is alpha, then the center of mass lies on the symmetry axis. Okay, somewhere here, such that in this case, this distance OC is given by the general formula. If this radius is r, it is given by the formula r sine alpha by 2 divided by alpha by 2. These are both derivations that we have done in the previous lecture. Okay. So these are formulae with derivations done in session 3. Okay. So now what we are having here is, okay, good. So now what we are having here is not the entire mass of that, but only a mass dm, which is of radius r, and this thing is of thickness dr. So where this mass dm center of mass is, it's located here. Okay. So this y coordinate will now be 2r by pi. It's not the center of mass of the whole disk, because the whole disk is consisting of more mass, but only that small part dm, it's located where it's located there. Okay. So this dm's y coordinate of the center of mass is this. Okay, so we are just borrowing a formula that we have already derived in the previous lecture, and that is very important over here, that you should understand that this is coming from the direct application of that formula. Okay. So once you understood this, now we need to substitute this and this in the formula for y cm of y of the whole semi disk. Okay. So coming back to the full semi disk, so therefore y cm for the semi disk, not the semi ring, this whole semi disk is being divided into semi rings like this, where we just saw semi ring. It has a dm of 2m upon capital R square into r dr, and the y coordinate of its center of mass is 2r by pi. Okay. So the center of mass of this semi disk now, that will be given by the formula integration y dm divided by total mass. So we will replace y with 2r by pi and dm with 2m by capital R square r dr. Okay. Now we are taking all the semi rings. So my semi rings are starting from the smallest one, which is right at the origin here. So for that one, radius is tending to 0, till the largest one, which is right at the circumference, which has a radius of capital R. So R is going from 0 to capital R. So this is integrated over all semi rings which are part of the disk. Okay. So now this integration has to be done, and as I told you, the integration is very easy. Just take all the constants outside. So 4m upon pi capital R square comes outside, and we are left with R square dr integrated from R equal to 0 to R equal to capital R, and this whole thing then divided by m. So this m cancels out with the numerator, so we are left with 4 upon pi R square integration R square dr from R equal to 0 to R equal to capital R. Okay. So this integration is R cubed by 3 from 0 to capital R. So that becomes 4 upon pi R square into R cubed by 3. So that finally gives me the y coordinate of the center of mass. Next step, we'll see that. Okay. So just make a note of this, people.
Can you show why that
Yes, so you have to. Sorry, come again, Vita.
Sir, can you show by that horizontal method also?
Yeah, we'll do that now. First, you note down this. Okay, let's come to the final step of this. Okay. And yeah, Norman, to answer your question, all these formulae, the standard formulae like center of mass or semi-ring, semi-disk, we have to memorize these. I will give you a list of the formulae which you have to memorize at the end. So this is 4r by 3 pi. Okay. This is semi-disk center of mass position. Okay. You can see r cube and r square in the denominator, it just cancels out, so it leaves r in the numerator. So it's 4r by 3 pi, whereas you will recall the position of center of mass of semi-ring that we just discussed. This was 2r by pi, but this is a ring, semi-ring, and this one is for semi-disk. So this is like a linear distribution. This is a surface distribution. So that's the difference between the two. Now, before we come to the other example of taking horizontal strips, I want to show you another interesting application. Okay. That is how we can to find area of a full disk or even a semi disk by integration. How we can do that. Okay. So you would have realized what has to be done here. We have a full disk like this. Now next what we should do is we should divide this into rings, thin rings. Okay. Right, so if we divide this, this full disk is divided into, this is a disk of radius r. So now we slice it into thin rings of radius small r and thickness dr. So you can see what is the area of the ring. It becomes circumference into thickness. So this is a thin ring of radius small r, thickness dr. Therefore, area equal to circumference into thickness. So again, this is that concept that you're taking a rod of length L and thickness dr, and we are bending it into a circular ring. So 2 pi r is equal to the length of the rod. So the area of this rod will be length into thickness now. But it's a small area because the thickness is small, so we are writing it like this. So that's how we get this, that the area of the ring is so much. Okay. So therefore, area of the disk will become integration of area of all rings. So integration of 2 pi r dr from the smallest ring right at the center, which is r equal to 0, to the outermost ring, which is capital R. So as you can see, this becomes this very simple integration. On substituting the limits and all that, we get the area of the disk as pi r square. So this is in fact a geometrical formula which we are proving by using calculus. Okay, now just as a quick sort of exercise in integration, I will show you the alternative method also, though it is not necessary per se. Okay. The alternative method of taking horizontal strips, you can actually try out these type of problems yourself also as an exercise in integration. So here, instead of slicing our disk into semi rings, if we slice it into horizontal strips, just the way we have to set up the integration will be a little bit more complicated. So what we'll have to do is, at a position y, we have to take a strip of thickness dy, and if you take this length as x, okay, and you can see the length of the strip will become 2x. So that is going to be 2x into dy. Okay. So the area of that strip is so much. Okay. So the mass of that strip will become sigma dA. So that is again 2m upon pi r square into 2x dy. Okay. So the position of the y coordinate of the entire semi disk, that will come from integration of y dm divided by total mass. So that will now be given by this thing, 4m upon pi r square into xy dy, because of this y, okay, divided by the total mass. Now we have to find the relation between x and y. So for the relation between x and y, you can understand, we'll use Pythagoras theorem. This radius is r, so you can see that x square plus y square is equal to r square. So we'll use the relation that x is square root of r square minus y square. Now this substitution is going to make the integration a little bit more complicated, which is why we avoid this as the primary derivation. Okay. So now this has to be substituted. So ycm will become, take the constants outside. Okay. From y equal to 0 to y equal to r. Okay. But now we substitute here this quantity, x is equal to square root of r square minus y square. So this will become 4 upon pi r square, because m cancels out. Okay. Now in the integration, it becomes y into x, which is r square minus y square dy. Okay. So further, to do this integration, we'll have to use a trick. Okay. So I'm coming to that. So here we can see that the integration is of this type. It is square root of r square minus y square into y dy. We have the y outside, where r is a constant, obviously. So for this type of integration, we can see that differentiation of y square is equal to 2y dy. Okay. So we make use of that over here. So therefore, if you take some new variable as r square minus y square, okay, or you take z square as r square minus y square, now differentiate both sides. So 2z dz becomes minus 2y dy. Okay. So that means y dy can be replaced as z dz. So this is the substitution we will use next. So in this integration further, we will substitute r square minus y square as a new variable z square. So that way, what will happen is minus 2y, there's a minus sign here, by mistake. Yeah. So minus 2y dy is equal to 2z dz. So we can replace y dy as minus z dz. And of course we can replace this. So the integration now becomes 4 upon pi r square is still outside. And the integration, I will replace y into dy as minus z dz. And I'll replace square root of r square plus y square. Sorry, r square minus y square. That will become z. So it becomes z into minus z dz. From y equal to 0. So that corresponds to z becoming how much? It corresponds to z becoming capital R. Okay, because you can see from this. Okay, to y equal to capital R, which corresponds to z becoming 0. Okay, so now my integral has become like this. Take the minus sign outside. Integral z square dz, but lower limit is z equal to capital R and upper limit is z equal to 0. So we'll complete this integration and we'll see that it gives us the same answer as before. But that's why we avoid taking the horizontal strips as the primary method, because the integration requires one further step of substitution. Okay, so
sir.
you can just take down the steps up to here and complete the integration. We'll do that in the end. Okay, so this is the alternate method. Okay, so we are taking dA as horizontal thin strips instead of semi-rings. So you can use this method to calculate the area also, like I've used the method of this rings to calculate the area of the disc also. So these are all like, part of standard methods in calculus. So as we proceed more in physics, you will learn some of these methods here. And of course, some of the methods you will learn in your class 12th mathematics also. Because after all, calculus as a pure mathematics subject is part of your 12th syllabus. This is more in terms of application of calculus in physics.
Sir,
Yes.
sir, but there will be different formula for all the cases. In
All the cases as in beta यहाँ पे देखो same formula आ रहा है ना, मतलब semi disc का तो obviously position of center of mass is independent of what method we use, no?
sir, for this
See
example,
what we are
I
getting,
am
minus. Acha, all different kind of shapes. Yeah, that's true, na? Every shape will have a different value of the formula, na, in the end of the day.
sir, so there will
So
be
for
one
example, if you take us, so there are certain formulae that we have to memorize as standard ones. The other ones will, if they come in the exam, they will come as derivation. So this will give the same formula at the end of the day for the semi-disk. But for example, if you take a semi-rhombus, I mean that's again a triangle, but or a different kind of shape, like a quarter disk or a disk subtending some arbitrary angle, again we will get a different formula. Harshita, it's not necessary to write the other method, but just as a practice in calculus, you can keep an understanding of how the steps work. For you, what is important at the end of the day is to remember these formulae: semi-ring, semi-disk, then arbitrary arc that we discussed, that r sine alpha by 2 wala formula. These are some of the standard formulae that you have to memorize. And also it is important to understand the methods for the derivation, so that if you get a derivation based question, you can do it yourself. If you get a question which is formula based, then you can directly substitute in the formula and do it. So at the end of this section, I will give you a list of formulae that you have to memorize, which will include some of these derivations that we are doing. Okay, next from the semi-disk, let us move on to examples of volume distributions. So in these type of examples, you have to take dm as rho dV, where rho is density or mass per unit volume. And dV is a volume element or a differential volume. So here we will start with the example of the cone. Okay. Okay. A solid cone made of material of uniform density. Okay. And also the cone has that regular shape. That its altitude is a symmetry axis. So our first example will be center of mass of a solid cone made of material of uniform density. Okay. So this height is capital H, let's say, and the radius of the base is capital R, and the total mass is m. So you can see from that the density of the cone will be mass upon volume. So 3m upon pi r square h, right? So this in itself will become a derivation we can do later. We can prove that the volume of the cone is given by the formula 1 by 3 pi r square h. The other thing is, if we take this as our y-axis, we can see that the altitude of the cone is the symmetry axis. There is three-dimensional symmetry about it this time. So you can see that the y-axis is the symmetry axis of the cone. Okay. Whereas the origin is the center of curvature of its base. Okay. The base being a disk in the XY plane, that kind of thing. So the center of mass will lie again on the y-axis somewhere. So we have to find the y coordinate of the center of mass. Its x and z coordinate will be 0. So center of mass lies on the symmetry axis. And to find y coordinate of center of mass, we need to do this integration. But here dm will be of the type rho dv. So the question is, what should we take as dv? What should be our volume element? Now this is pretty straightforward. You can understand it yourself. What kind of volume element we should cut over here? Keeping in mind that the y-axis is the symmetry axis, we should cut it into slices. Imagine we've taken a plane parallel to the xz plane. So this is the xz plane. So we should cut slices which are parallel to the xz plane. So the volume element should be thin discs sliced by a plane parallel to the base. So that's how we should slice the cone. Okay. So basically what we should do is we should slice this cone into thin discs like this. Which have less thickness. Which have thickness dy. And which has a radius, let's say small r. Okay. So these discs are like this. Okay. They are of radius small r and thickness dy. So their volume will become area into thickness. Now again, there's a bit of discrepancy here, because if you look at the proper shape of the disc, it's not exactly a disc. It's got a slight amount of slant on the side. But as long as the thickness is less, we can neglect it. Okay. We are treating it like a disc like this, which has got a straight side like this, like a slice out of a cylinder. But actually, the disc is more like this. It's got a slanted side. But the slanted side can be ignored as long as the thickness is very less. This thickness is dy and this radius is r. So we are almost treating it like this one above. We're ignoring the slight slant on the side. Okay, so now again for convenience, what we will do is we will take this time the distance of the disc from the top apex rather than from the bottom. Okay. I'll just show you why that will be more convenient. We'll take the position in terms of, now I'm making a two-dimensional diagram just for convenience. Okay. But obviously you understand that this is the side view of the cone. So it's actually a three-dimensional thing. Okay. Okay. So instead of taking the position with respect to the bottom point, which I had taken originally as my origin, now I'll take this point as our origin. We'll take the downward axis as our y-axis. So we will take the position of this disk at a distance y and its thickness as dy and its radius as small r. So what that will do is that will give us the similar triangle concept over here, that this radius is capital R. So we can see, and this total height was capital H now. This height was capital H. So we can see that H by R is the same thing as Y by small r. So the radius can be written as R by H times Y. So the volume of this disk, which we had just written just now, was pi r square into thickness. So that will be expressed now as pi into R by H times Y. So its mass is density into volume. So density was 3m upon pi capital R square H. Into the volume now is this quantity. So it becomes this kind of term, 3m upon H cube into y square dy. Pi r square cancels out. Okay. So we get this. So now the y coordinate of the center of mass of the cone becomes integration of y dm divided by dm, integrated over all disks. Now this zone center of mass is lying here only now. So the y coordinate is just the y coordinate of the disk itself. So we let that be, and we replace dm with this term, 3m upon h cube y square dy. Okay. And this is for all disks. So it's going from the disk right at the top where y is 0, the disk right at the bottom where y is equal to capital H. Okay. So this is integrated over all disks divided by mass. So take the constants outside, 3m upon h cube. Then this integration becomes y cube dy from y equal to 0 to y equal to h divided by the mass. So m also cancels out. The same type of integration that we've been doing so far. So this becomes 3 upon h cube into integration y cube dy from y equal to 0 to y equal to h. So you see that from the apex of the cone, the center of mass is at 3/4 the height. So you can say that the center of mass is at 3/4 h from the apex. Okay, or that's the same thing as at h/4 above the base. So that becomes our final conclusion, that the center of mass of the cone that is a point like this, which lies from this point, it is at a height of h by 4, or from the apex, it is at 3 by 4h. This is the case for the solid cone. And this is another direct formula that you should remember. Yes. That is correct. Now, incidentally, you can also derive the volume of a cone using this. Okay. To derive formula for volume of a cone. Okay. So we'll just borrow the same diagram, but instead of integrating for center of mass position, we will integrate for just the volume.
Sir, can you show that?
Yeah, I'll just come back there. So this shows that it is 1 by 3 pi r square h. Okay, so just make a review of this quickly and make sure you understand the steps. Okay. Tell me if there's any doubt, we'll discuss. So it's important that you understand the method as well as you remember the final formula of the position of center of mass of solid cone also.
Sir,
Yes.
sir, what did you write over there? Center of mass is at 3 by 4h from apex or at h by 4 above?
Box.
Base.
Okay.
From the base, the height is that much. Correct?
Yes, sir. Correct.
Okay, so hope the calculation of center of mass part is clear. Now let's come to the calculation of volume of a cone using this.
Sir,
Yes.
sir, could you just hold up for a moment? I think I missed something.
Yeah.
Sir, 1 minute, please.
Yeah.
Done, sir.
Okay, so this is done, I hope.
Yes, sir, done.
Yes, sir.
Okay. Now we will continue with some more center of mass examples, but we will come back to them later. Now we will move on to another part of this chapter, which is about motion of center of mass. So in the next lecture, we will come back to position of center of mass once more, and we will also see center of mass of hollow conical shell, then hollow hemispherical shell, like a hollow hemispherical board, then solid hemisphere. So we'll come back to these later. Okay. So these we'll look at in the next lecture. So you can also try out, the derivations yourself, or you can see them in reference books like H.C. Verma, etc., and try to understand the steps yourself. Okay. Currently, we will move on to the next part, which is motion of center of mass. Okay. So it's pretty easy to understand that if we have a system of particles, whether it is continuous or discrete particle system, but there is motion of the individual particles, then the center of mass should also be moving. Okay, so for example, if we have a situation where, think of the most basic type of system, we have two particles of identical mass, let's say. Okay. So particles A and B, they are of identical mass m, but now one of them starts moving with some velocity, and let's just say for argument's sake that it's moving along the same axis as the line joining the two particles. Okay. So what will happen is that if t equal to 0, the center of mass was located here. Okay, this is the situation. So the center of mass is here. It is, let's say, dividing this line by 2. The distance between these two is x0. Okay, and the particle A is at rest, whereas B is moving with uniform motion. So it has a uniform velocity. So what we can observe is that after some time t, how will this system have evolved? The particle A would have remained where it is, but B would have moved from this position to somewhere here, let's say. So B would have made a displacement now of displacement of B would be the change in its x coordinate, which would be V0 into t. So the distance between A and B would have now increased to x0 plus V0 t. So the center of mass accordingly would have moved from here to here, where this distance would be half of this. So therefore, if we compare the original position of the center of mass with the new position of the center of mass, you can see the center of mass has moved by how much? It has moved by V0 t by 2. So it has in fact moved by half the displacement that B has moved. So in this particular example, we can see that because the two particles are of equal mass and the motion is happening in this way, we can see that center of mass moves with a velocity which is half the velocity of B in this case, when something like this happens. This we can just understand intuitively. Because after some time, here the center of mass was over here. Now the center of mass is over here. So the center of mass would develop a velocity which would be V0 by 2. But this was just logically understanding from the fact that the center of mass always lies at the midpoint of A and B. But if it's a more general situation with more number of particles involved and more sort of random directions of motion, we need not always move along this axis. It could move with any sort of diagonal sort of direction also. Then how do we find the velocity of the center of mass? So for that, we have to look at a more systematic derivation, and we'll come to that next. But note down this example first. Yeah, Norman, just follow the first diagram. So in this, you can see that the center of mass is at a distance of x0 by 2 from the particle A. And the second diagram, what is happening? The center of mass's distance is increasing from A to x0 plus v0 by 2. Na? So what is the change in the x coordinate of the center of mass? It is the final position, which is x0 plus v0 t by 2 minus the initial position, which was x0 by 2. So it's v0 t by 2. Okay, so that is nothing but velocity of the center of mass into time. So you can see that VCM is v0 by 2. Now let's take another example. Again, we have this two particle system. And again, they're of equal mass. And this distance is x0 at t equal to 0. But this time, A and B are moving with uniform velocities in opposite directions like this. So this one is moving with some velocity in this direction, and this one is moving with some velocity in this direction. So VB is equal to, let's say, 5 centimeters per second in that direction, whereas VA is, let us say, 3 centimeters per second. Okay. So A and B move with opposite uniform velocities as shown. Okay. Find the velocity of the center of mass. Just try this out. Try this logical method that we were discussing last. So anybody got the answer? So see, if we're here at t equal to 0, then after some time, okay, the situation would have changed. And B would have moved from here to somewhere over here, let's say. So B would have moved by displacement of 5t in centimeters at time t, whereas A would have moved by a lesser displacement, because this is moving at 5 centimeters per second. This is moving at 3 centimeters per second. So A would have moved by a lesser displacement of 3t. Okay. So in the original diagram, the center of mass of the system was here. Now in this new diagram, what has happened? The distance between A and B, that has increased to how much? That has increased to x0 plus 8t, isn't it? where which is x naught. So where is the center of mass now located? The center of mass is now located at some position like this, where this distance is equal to this distance. Okay. So now from this, can we calculate the displacement of the center of mass? It's a bit of a calculation. Okay. I mean, we'll have to apply ourselves a little carefully here, but we'll see this will become the displacement of the center of mass. So how we'll calculate this? See, this much is how much? It is x naught by 2. Okay. So this value here, which is 3t, plus this value, which is x naught by 2, plus this value, which is delta x of the center of mass, the displacement of the center of mass, this should be equal to this value below, which I've written, which is x naught by 2 plus 4t. Okay. So from that we can see that 3t plus delta x is equal to 4t. That means delta x is just t, which is velocity of center of mass into time. So we should be getting the velocity of the center of mass as 1 centimeter per second. So we understand that the center of mass here will be traveling in this direction, okay, which will be for this particular data, this VCM will come out to be 1 centimeter per second. Okay. So A and B were located here initially, where this distance was x naught. Now after some time, A has moved here, B has moved here. So this distance has increased to x naught plus 8t. Okay. So the center of mass has gone from this position to now this position. Okay. And from this, we calculated the displacement of the center of mass. Okay, so as you can see, if there is more complication in the direction of velocity and all that, this type of geometrical calculation is going to become more tricky, right? So we have to develop a better formula-based method. So now let us understand, back to motion of center of mass in general, how to develop the general formulae. So in kinematics, we have a formula that displacement is equal to change in position. It is final position minus initial position. So here we will calculate displacement of center of mass by using this same kind of formula, but by applying it to the position of the center of mass. So displacement of the center of mass should be the change in the position of the center of mass. Now earlier we had seen the position of the center of mass for a discrete particle system is given as summation mr divided by summation m. Okay. So accordingly, the displacement of the center of mass is delta of this quantity, summation mr divided by summation m. Okay. Now notice that these are constant. Okay. The mass of individual particles is not changing with time, we are assuming. It's not like an exploding system or something like that. Okay. So therefore, in the next step, what will happen? This formula for change, it will go into the bracket and it will apply to position. It's only positions which are changing. The masses are remaining constant. It's basically like saying for a two-particle system, we just compare this general formula with a two-particle system. The position of center of mass is given by m1 r1 plus m2 r2 divided by m1 plus m2. So the displacement of the center of mass is change in position. It will be given by change in this quantity m1 r1 plus m2 r2 divided by m1 plus m2. Now here m1 and m2 are constant. Okay. Whereas r1 and r2, the positions of the individual particles, they are instantaneous. Okay. So therefore, when we take this delta inside the bracket, it just becomes m1 into delta r1 plus m2 into delta r2 divided by m1 plus m2. Okay. So the equivalent step of that in a multi-particle system, in an n-particle system, is this. Instead of two particles, if we are summing up over n number of particles, then it's this. Okay. But now notice that delta Ri is nothing but displacement of the ith particle. Change in position is displacement. So the formula for displacement of center of mass becomes symmetrical to the formula of position. It is summation of m into s divided by summation of m. Okay. Or here, the displacement of the center of mass for two particle system is m1 s1 plus m2 s2 divided by m1 plus m2. Okay. And you can see if we apply this to our two examples above of the two particles A and B, we'll get the same results which we had got geometrically. So this becomes our first formula in this series of equations that define the motion of the center of mass. Now, the first thing that we study in kinematics in motion is the definition of displacement. So here it is the displacement of the center of mass. Displacement of center of mass in terms of the individual displacements of the particles is given by this particular formula. So just make a note of this, people.
Done, sir.
Right. Okay, so now you can see that if we applied this to the previous question, how we would very easily get this, that the two particles A and B were of same mass, but after some time A had displaced by B had displaced by plus 5t, okay, and A had displaced by minus 3t because it was in this direction. So displacement of center of mass would be m into displacement of B plus m into displacement of A because they were equal mass divided by m plus m. So it should be the arithmetic mean of their displacements. So this was minus 3t, this was plus 5t. So that's why it was coming out to be t. And that's why the velocity of the center of mass was coming out to be plus 1. Okay. So this was the previous example applied over here. Okay, anyhow, now let's move on to the next thing in our derivation. Okay. So in kinematics, after displacement, the next parameter we define is velocity.
Sir, could you just scroll up?
Velocity of, sorry? Yeah, what did you ask, beta?
Sir, could you just scroll up? I missed the last point.
Okay. This part, the example.
Yes, sir, that which you wrote on the right.
Okay.
Done, sir.
Okay.
Sir, 1 minute.
Yeah.
Done, sir.
Okay. So next, let's come to the velocity of center of mass concept. So velocity is defined as rate of change of position, instantaneous rate of change. So in this case, that becomes instantaneous rate of change of summation mr divided by summation m. Okay. Where again, you can see that these are constant, whereas the position, they are instantaneous. So just like the displacement, but here the operator is rate of change instead of change, instead of delta applying to this bracket, what is applying is rate of change. So the rate of change goes inside the bracket, and that over here becomes, so it becomes summation of m into rate of change of position, because m is constant, divided by summation of m. And the rate of change of position of the ith particle is nothing but the individual velocity of the ith particle. This is the instantaneous velocity of that particle mi. So again, this formula also becomes symmetrical, that the instantaneous velocity of center of mass is given by summation of mass into velocity of individual particles divided by the total mass. So this is going to be a more significant formula for us. We'll discuss compared to the displacement formula. This is even more significant. Okay, so let's see one important implication of this next. So once you got this velocity, now in this you understand that summation of mass in the denominator we can just write as capital M, which is the total mass. So bringing it to the left hand side, total mass into velocity of center of mass is summation of M into V from I equal to 1 to N. So now this quantity, total mass into velocity of center of mass, this will be defined as the momentum of the system. This will be defined as linear momentum of the system of particles. That is defined as total mass into velocity of center of mass. And we can therefore see that the total momentum of the system is equal to the vector sum of the momenta of the individual particles. Okay. Or total mass into velocity of center of mass is summation of M into V. So this is another important concept over here. That when we define the momentum of the system as total mass into velocity of center of mass into instantaneous velocity of center of mass, okay, we can define it as a formula also as the vector sum of the individual momenta, P1 plus P2 plus P3 added up to nth particle. So now see why this final relation of momentum of system is important is because momentum is always related with force. The external force on a system is equal to the rate of change of its momentum. So next up, when we analyze this equation further with rate of change on either side, we will actually be analyzing the Newton's second law application for system of particles. Okay, so we'll come to that again, but that is why it's significant and important that we understand definition of momentum of a system. It is total mass into instantaneous velocity of center of mass. That is capital M into VCM. And it can also be calculated as the vector sum of the individual momenta of the particles. Okay, so on this important final relation over here, we will conclude today's lecture. Okay. And we will continue next time with more applications of this. And with those applications, we will be getting into application of Newton's second law for a system of particles and also into the kind of situations where momentum of a system is conserved because the net external force is zero. So that is in general, those are called momentum conservation situations. So they are important applications in this chapter of center of mass or system of particles. So we'll be discussing all those things in the next lecture coming up. Meanwhile, please do revise the derivations of center of mass that we've done today, the position of center of mass calculation, and do questions from HC Verma and your module which are related to position of center of mass. So So that's it for today's session, people. Wish you all the best.